Okay, here in section 7.7, our task was to basically introduce this thing called a natural logarithm. And a logarithm, like the common logarithm, has a base 10. The natural logarithm has base e. And in the book, it's described as an irrational number that's similar to pi, the square root of 2, etc., etc. So, with that said, the natural log and the normal logarithm are really similar in that we can go from one form to the next in terms of a natural logarithm and an exponential function. So the first part here says write each exponential equation in log form. So we can say that e, this irrational number e, is my base of ln. ln stands for the natural logarithm, with base e of 8 equals x. And you can easily verify this by implementing your log loop. And indeed, e to the x equals 8 is the problem that we initially began with. Now, let's try the next one. Same base, e, natural log base e of x equals 5. Double check, e to the 5 equals x. There we go. Same is true now, go in the other direction. As long as we can understand that a natural log without any base, it indicates e. It's indicated by e. So we could say that e raised to this power, going from log to exponential, we could say e to the 0.7741, that equals the natural log of x. Oh, excuse me, no it doesn't. Sorry about that. It equals x. Okay, let's try this one over here. E to the power of x equals 10. Alright. The logarithm properties you learned also apply to the natural logs. The following log expressions can be simplified into a single logarithmic term. You also have a natural log button on your calculator so that you can find the decimal equivalent of these expressions. So indeed, a scientific or graphing calculator will be helpful to solve these problems here. So 3 times the natural log of 10 minus the natural log of 8. So first things first, we're going to take this 3 and replace it on top of the 10. So the natural log of 10 to the third power minus the natural log of 8. And then we could rewrite this as a single log, a natural log, of 10 to the third, which is 1,000, over 8. Because of the subtraction sign, we can implement the quotient property. And from here, we can take the quotient of 1,000 divided by 8, and you get 125. So the natural log of 125 on your calculator now, the ln button is underneath the log logarithm button, and you can say the natural log of 125 is approximately 4.828. Okay. The next one. The number on the front represents the exponent, and so the natural log of 3 squared plus the natural log of 4 plus the natural log of y. Now because all of these are plus signs, that implements the product property, and we could rewrite it as 1 log. 3 squared is 9 times 4, which is 36, and then times y here. And there you have it. Exponential equations that have base e are easier to solve if you use the natural logs, because the natural log of e equals 1. If you go to this fact, the ln of e equals 1, and that's true because of my base here, e to the 1 power equals e. So whenever we see an exponential equation that has... Okay, so when I solve these equations, I want to first and foremost isolate my base, which again I've underlined to be e. And so if I'm going to isolate my base, the first thing I will do is add 5 to the other side to make 8. And then dividing both sides by 4, I get e raised to the power of negative 2x equals 2. At this moment, we can take, like the other day, we can take the log of both sides, but here, because of base e, we will take the natural log of both sides, like so. And just like our property rule, our exponent property rule, we could bring out this exponent of negative 2x out in the front, and we have the natural log base e of e, which is 1. Going back up to here. So with your calculators, you will say the natural log of 2 divided by negative 2. And let's see what we get. Let's see here. The natural log of 2, and divide that by negative 2. You should get approximately negative 0.347. Okay, go ahead and try the next one. Okay, so beginning the next one here, I found myself isolating to get to the base, which is e. I get e to the negative x equals 9 over 5. Now I will go ahead and take the natural log of both sides. Swing the exponent out in the front. And I didn't rewrite ln e right here. And why didn't I do that? Because the ln of e is 1. And to truly figure out my problem or my solution now, I have to divide both sides or multiply by negative 1. So x equals the natural log of 9/5 times negative 1 for an answer of negative 0.588. Okay, now we're going to solve logarithmic equations that are not written as exponential functions, but we can get there. I'm going to show you what I mean. So the first things first, let's isolate the natural log. So we need to divide both sides by 3, and we get the natural log of 4x equals 8. At this moment, we have to understand that my base is e, and because of the fact we only have one natural log involved, we can rewrite it using the log loop. We can say that, hey, e to the 8th power equals 4x, and if we're solving for x, we can divide both sides and get something that looks like this. Now e, let's see, there is a button E on your calculator. It's the shift division button. It's the shift divide. So if I do shift E and I raise it to the power of 8, I will take that number and divide it by 4 to get a value of 745.239. Now there also is an e to the x button, which is the natural log, shift natural log, and that takes the base e and the cursor automatically goes up into the exponent. So you could go that route as well. Let's try the next one. Now the next one, we can immediately begin with our log loop because the natural log is isolated. Therefore, we have e to the 4 equals, let's see, this quantity x minus 8 to the 4th power. I'm solving for x, and it's being raised, a quantity, it's involved in a quantity being raised to the 4th power. So what I will do is I will take the 4th root of both sides. So x minus 8 equals the 4th root of e to the 4 is simply e. Add 8 to the other side. E plus 8 is equal to 10.718. There are some cases in which interest can be compounded continuously. If you see this word in a word problem, a finance problem, interest being compounded continuously, we will use this formula, A equals PE to the RT, where P is still the amount at the beginning, or the principal, R is the rate, written as a decimal, and T is time. E, again, is that growth rate, because it's above 1, 2.718. So we're going to use this PERT formula. P-E-R-T is another acronym of PERT. So we're going to use PERT formula to calculate the following. Madeline was born. Her grandparents deposited $3,000 into a college savings account. So right away, I will say, hey, $3,000, that's my principal. The account pays 4% interest. There's my rate, compounded, and then here's the word, continuously. So right off the bat, I know I will use P times E raised to the RT. What will be the balance after 10 years? That's my time. A equals my deposit, base E raised to the 0.04 times 10. So the amount at the end, we can punch this in one shot. 3,000 E to the 0.04 times 10. Make sure you have parentheses if you're going to do that in one shot. And so we see we have, oops, try that again, 3,000 to the 0.04 times 10 to get a total of 4,000, this is a dollar symbol, 4,475 and 47 cents. So go back, pause the video, and make sure you get this value after you plug it into your calculators. Okay, how long will it take the balance to reach at least $10,000? How long? Time. That's what we're solving for now. If we're solving for something that's in the exponent and we have base E, we can assume we're going to be taking the natural log of something for both sides. How long will it take the balance to reach? $10,000, the amount at the end. So here we go. $10,000 equals my principal, $3,000, times E to the RT. My rate didn't change. And T is what I'm trying to solve for now. So first things first, let's divide both sides by 3,000. And I have 10 over 3 equals E to the 0.04 T. Now we're in a situation, just like the previous couple pages here, where we can now take the ln of both sides. The ln of E is 1, so I'm left with 0.04 T equals the natural log of 10/3. So to solve for T, I will divide the natural log of 10 over 3 by 0.04, and T equals, I'm kind of going out of bounds here, guys, but you get the point. The natural log of 10/3 with your calculator, that value divided by 0.04 gives me approximately 0.1, and then years. So in about approximately 30 years, her balance will be $10,000 if we deposit $3,000 initially. Now, the last part says, hey, if Madeline's grandparents want the balance to be $10,000 when she is 18 years old, how much money do they need to invest? So here, they're asking us, how much money do they need to invest? Right here, they're asking for the principal. How much should we put down if we want her to have at least $10,000 when she's 18? She can take the money and go do whatever she wants with it. Let's see. My principal, or excuse me, the money at the end, after 18 years, 10 grand, equals P times E to the 0.04 times T, which is 18 years old. And so what we can do is we can multiply 0.04 times 18, and we'll get 0.72. So 10,000 equals my principal times E to the 0.72. Okay. Now E to the 0.72 is a value. I can find that value by taking E to the power of 0.72 and then take 10,000. Essentially put here, guys, this is what we're doing. We're dividing both sides by E to the 0.72. So the principal equals 10,000 divided by E to the 0.72, which comes out to be $4,867.52. That's the amount of money that Madeline's grandparents would have to invest today if 18 years later, on her birthday, she can have 10 grand. Okay.